Today's topic will be machine learning applications in the retail space. We'll discuss how it can be used to increase average order value, as well as how it can be applied to optimize inventory and supply chain management. Our presenters today will be Phil Horowitz and Joe Rose. Phil is not only JBS's chief architect, he is also the founder of our open source practice, chair of our architecture group, and an industry veteran with over 20 years of experience. Phil holds both a bachelor's in computer science and a bachelor's in mathematics from University of Pennsylvania. Joe is our senior vice president of delivery and has over 11 years of experience with retail, e-commerce, and multimedia applications, web applications. Joe holds a bachelor's and master's degree in computer science from Georgia Southern University. With the introductions out of the way, Joe, would you mind taking us into an overview of the presentation today?
Sure. So today we're going to talk about machine learning in general, what it is and how it's applied. We'll keep it pretty brief there so it's not too academic. And then we'll look at some specific use cases for machine learning that apply very well in the retail space. So specifically product recommendations, inventory and supply chain management, buyer segmentation, fraud detection. And we'll wrap up with some overall do's and don'ts and best practices and learnings. So first, let's dive into the overview. So machine learning or AI in general, it's one of the more overhyped, overpromised, and underdelivered fields of computing, I'd say, in the last 30 years. There used to be this sense that if you take all of your data and you stick it into a computer and you flip on the AI switch, the computer would just start making all of your decisions for you. And that has never been the case. It's been tried and failed numerous times for numerous different applications, and it's not anywhere near kind of the idea that we all have in our head of what AI is, which is a science fiction movie of controlling Terminator machines or something silly like that. So what's changed? Why are we in this webinar saying that these technologies are now something that you should consider? Well, there's a good bit that's changed. The first is that we've learned a lot more about what types of problems AI can solve. There are a lot of problems that if you're specific enough and the data you feed in is specific enough and the results that you expect out are specific enough, AI does an outstanding job of decision making, better than a human being. There's also been a lot more practical knowledge in terms of, PhDs in computer science may have known about all these algorithms and how they apply, what types of data they accept. But the practical application of this problem in retail or this problem in e-commerce or this problem in business aligns well to this algorithm and this type of data. So there's kind of been an establishment of industry best practices that help us use these algorithms, even though some of them have been around for quite some time. The best practices around it, how to do it well, have been more developed. And then finally, one of the remaining unlocks, if you will, that has made it more applicable and readily available is that the implementation of these algorithms, actually coding them up, used to be something that you'd have to have a team of 20 data scientists and a bunch of hardware and solve the problem that way. And that's a very high barrier to entry. It wasn't practically accessible for most folks. And most of the cloud providers, so AWS, Google Cloud, Azure, and so on, now have working APIs and implementations of a lot of these algorithms that make it almost as simple as feed data in, get results out. So it's a lot closer to the promise that I alluded to at the beginning of the conversation. So the arena and the effectiveness of ML and AI in retail is a lot different now than I think it was 5 or 10 years ago. So coming to this, you should have a different sense that it's not what it used to be. So with that, I'll turn it over to Phil, and he can give us some more specifics on what that means.
Thanks, Joe. So now I'm about to probably give the what may be the record for the briefest overview of machine learning. And really, there's only two things that I'm going to discuss in this overview, and that is a a very succinct definition of what machine learning is and the typical patterns that you see when you're embarking on a machine learning project. So as far as what machine learning is, and in essence, it's bigger brothers, reinforcement learning and deep learning, they're a class of computer algorithms that improve automatically through experience. And for our purposes, the experience, the word experience in that definition, it quite simply means data. And the more data we can feed into these algorithms, the better they're going to get. Their predictions are going to be more accurate, and they're going to be able to forecast more accurately and more efficiently. And so kind of inherent in that definition is the idea of we're going to need a lot of data to put into these things to get the kinds of results out of them that we want. Next, from a more pragmatic project standpoint, in terms of how machine learning applications are typically built, in a way they're very similar to how your normal retail applications or normal kind of IT or enterprise applications may be built. And there's a series of steps that you typically see in a typical ML projects. And like most, there's some kind of problem identification and understanding the problem you're trying to solve. And then we move on to what is really actually the biggest step, and that would be data preparation and data engineering. And that is absolutely vital to making sure that we get good results out of our machine learning models. The bulk of most machine learning projects is actually spent in this step here, your data prep and your data engineering. Once you have your data that you'd like to use, we kind of enter this loop of model selection, training and testing our data on our model, and then tuning our model. And we loop through those three steps until we get an output that is acceptable for what we're looking for. And then once we get to that point, we operationalize our model. And it's very similar to operationalizing almost any IT application. There's deployment. We need to make sure that all of our operational aspects are in place: monitoring, logging, error handling, reliability and fault tolerance. All these things are relevant for a machine learning project, just as they are any other kind of project that we would typically see in a retail environment.
So one of the specific things that we're going to talk about in terms of use cases for ML is product recommendations, and this is an interesting one. It's one of the easier ones, I would say, to get into because the data that you need to drive it essentially is customer data and sales data. And most retailers and most e-commerce sites have a wealth of existing customer and sales data. So it's rare that you get into it and say, we have to go build a bunch of data collection things to be able to support the machine learning and gather up a body of data before we can do it. Usually the data you have on hand is sufficient to build out the recommendation system. It's also very effective. It's one of the better algorithms in terms of comparing it to, say, a hard-coded recommendation engine or a rule-based engine. It does a much, much better job. The delta that you will see between the effectiveness of an existing non-ML-based system and an ML-based system is surprising. It's a big gap. What's also interesting is you don't necessarily have to optimize purely for revenue or transaction volume. You can make whatever goal metric you like the so-called result for the product recommendation. So you could drive revenue, or you could drive margin, or you could drive AOV, or you could drive inventory. So one of the more interesting ones that we've done is putting in the cost of carrying inventory and a cost associated with carrying multiple SKUs and saying it'd be cool if the product recommendation engine recommended things that were overstocked or things that we were trying to deplete out of inventory to shift sales to those items to drive down inventory costs. So you don't necessarily have to think of a product recommendation engine solely as, hey, we do this to drive a higher conversion rate or solely to drive revenue. So there are other things you can optimize for. And I think, Phil, you have some specific business cases that you had seen some information on that you wanted to cover.
Right. So looking at this slide, I think these kind of statistics speak for themselves. 35% of all of Amazon.com's revenue comes from an ML-based product recommendation system. Likewise, with Netflix, 70% of the content that is viewed on Netflix is coming from their own recommendation system. And as a matter of fact, I think it's interesting, Netflix themselves feel that if you actually need to type in a search and actually do a search by hand, they actually feel that that's a failure on their part. Because ideally, any customer that logs onto Netflix to use something, to view something, there should be enough relevant recommendations in that customer's queue to never have to search for something by hand. So I think that's I think those statistics speak for themselves as to the importance of having a good product recommendation engine and strategy in place. So when it comes to product recommendations, there's generally two ways that are typically used, and these are collaborative filtering and content-based systems. And collaborative filtering is really based on the idea of co-occurrences, and co-occurrences is really just kind of a fancy word for two or more things that are going to occur together. And in this case, the things that we're looking at are users and products. So the idea is that I have a customer that has bought a certain amount of products, and I'm going to compare him with the rest of my customer base, see what kinds of products that they may have purchased, see what kind of similarities I may find for this particular user, and then extrapolate based on that what my recommendations should be. And in terms of approach, collaborative filtering is always where you should probably start first if you're first embarking on building out a recommendation engine or incorporating one into your existing retail applications. It's very tried and true, and it's very easy to get up and running. And it's very easy to understand, too, in terms of how it works and what is happening under the cover, so to speak. There are some issues, though. First, it could be difficult to scale. If I have a customer and I'm constantly making comparisons to all my other customers, you can start crunching a lot of data very quickly, and it can be difficult to scale. It also suffers from a common issue that recommendations suffer from, and that's called the cold start problem. And essentially what that means is that we have a new customer coming to our site, our store. He has no prior data, no prior transactions, prior purchases, so we don't know exactly what to recommend for this customer. And the last drawback, and this one actually is quite important, is that collaborative filtering doesn't lend itself to recommending products based on personalization or behavior information of our customers. So we can't take into account the data that makes a particular customer unique relative to our other customers and then incorporate that into our recommendations. So in order to offset some of these issues with collaborative filtering, there's another approach, and that's content-based systems. Content-based systems, as the name explains, it's based on the content either of our customers or content either of our products. And it allows us to incorporate a lot more features of data into our recommendation algorithms to come up with more accurate recommendations. So unlike collaborative filtering with content-based methods, it's much easier to incorporate behavior data in the form of clickstream analytics. How long has this person been on this page? What are the unique things about his customer profile that we can use for recommendations? And also product descriptions, product ratings, product reviews. With content-based methods, they allow us to enable data sets that contain all this information to become inputs into our recommendation systems as well. Usually, as your ML and data expertise grows and more experience is acquired, you generally want to go with hybrid approaches that use the best of both of these kinds of systems.
So one of the places where we implemented this was at a customer of ours called Wine Access. And what's interesting there is not just the results that they saw specifically from this. So with this, they saw conversion rate for product recommendations grow 175% in 5 months, which is an incredible result. They were not exclusively focused on growing revenue. They were also focusing on inventory management and inventory optimization. So they saw a twofold benefit out of this. They recommended like products that a user was more likely to buy, and they recommended products that had a carrying cost, an inventory cost, that when those came off the shelves, they saw a nice cost reduction. So it was actually a larger revenue driver, or not revenue driver, margin driver for them than you would otherwise think. Previously, they had used product recommendations to just get rid of stuff. Or the way they were convincing people to buy it was just to make it very, very cheap. So that was a big deal. Overall, the company a couple of years ago didn't embrace machine learning or using statistics to drive decision making. And I'd say within the last year or two, that became a primary focus of how they drive business. So as a result of that, as a result of the product recommendation engine, as a result of, transparently, of COVID and it driving larger alcohol sales, they did see an increase in overall revenue of 170%. And what they think happened there is some of that was driven by COVID. They think a lot of it was driven by their reliance on these type of techniques to grow revenue. And we don't call it out here, but they've also used some other things in terms of inventory management and such to drive margin increases, margin percentage increases at the same time.
Okay, so one of the things that I want to bring up is that in addition to just talking about these problems and how ML can work to help solve them, I do, throughout our presentation here, we want to recommend some ways to incorporate these techniques with very low barriers to entry. So we're going to be making some technology recommendations that will enable you to bring these kinds of techniques into your own applications relatively easily. And we're going to start with AWS Personalize. And essentially, AWS Personalize is a fully managed cloud-based service that is actually the same set of technologies that powers Amazon's own product recommendation engine. It's very tried and it's very true. It's had one of the absolute largest e-com data sets of all time to help make it really top notch with its recommendation. So in addition to it being able to recommend products with a great deal of accuracy, it's very simple to integrate. It has a very standard JSON API that you can integrate it right into your existing systems, or obviously incorporate into new ones that may be built. But it's a very low barrier entry to incorporate into your existing IT infrastructure. And in terms of, again, this low barrier entry, it automates quite a bit of the actual data science that goes into leveraging ML solutions. So selecting the model, tuning the model, training it, testing it, and then ultimately deploying the model and getting all those operational aspects in place that I mentioned before, such as the monitoring, the logging, and whatnot. AWS Personalize handles all these things for you. So if you don't have a data science department, or if you don't have a dedicated data engineering staff, you're still able to bring these things into your applications and start taking advantage of them. In addition, what's nice is that out of the box, it also handles the cold start problem that I mentioned earlier with collaborative filtering. And it also does real-time recommendations. So it can incorporate user activity, some of that behavioral data that I was talking about, and it can do it as they're literally moving along on your site. And of course, another thing that makes it really appealing is that it integrates not just websites or web applications, but mobile apps, SMS, and email marketing systems.
So this is another cool use case for ML, inventory and supply chain optimization. So this is essentially managing the purchasing of your inventory based on sales data and current inventory level on shelves, and making sure that you don't have empty shelves anywhere, and you don't have shelves that are too full. Prior to COVID, these algorithms did see a decent sized jump in the ability to improve over a rule-based system or some of the more classic mechanisms of inventory management. And they were worth pursuing for retailers, obviously, because inventory tends to be one of your most expensive carrying costs. What happened with COVID, obviously, was there was a ton of supply chain disruption. And the machine learning algorithms really started to differentiate themselves in a much more material way. They are much better at predicting and accounting for supply chain disruption when you feed in the appropriate data than any of the off-the-shelf classical inventory management systems that don't implement ML. So what used to be something that was a nice cost-benefit turned into something that's almost a must-have in terms of optimizing inventory levels and controlling waste and not having, especially if you have, one of the areas where this is really, really effective is if you have perishable goods. Having better inventory management obviously helps reduce waste significantly. And then the other thing that it lets you do is get closer to a just-in-time or an on-demand inventory management model, which has its own set of benefits specifically around carrying costs of inventory and size of warehouses and things like that. So with that, I think, Phil, you'll dive into some details there and talk more specifics.
Sure. Thanks, Joe. So first off, just a couple of more stats. And based on some studies that have been done, ML-enabled supply chain management really can drastically reduce forecasting errors. 50% is quite a bit. And they also help scale back inventory and reduce lost sales by 50% or more. And as Joe mentioned, excess inventory and mismanagement of inventory is a great way to tie up cash. So those stats kind of speak for themselves, and they're great, in incorporating ML solutions into your inventory optimization strategy can be a really, really great way to manage that a lot better and save a whole lot of money. So before I dive into some of the benefits that we get from ML solutions in this area, I do want to briefly talk about some of the drawbacks of more traditional methods. And there's a few. And first, it's very, as Joe mentioned, most traditional inventory methods are rules-based. And as such, for more complex and especially dynamic factors, it's very difficult to encode that into a set of rules that are easily manageable. And unfortunately, it's these complex or more dynamic factors that greatly influence how we can keep our inventory or stock optimized. So in addition to that, another drawback with most rules-based traditional inventory systems is that they're based on the idea of continuous demand. And with that, they usually give a much higher weight to more recent data because they want to capture more recent trends. And that in itself is not necessarily a bad thing, but it does create a lot of limitations in many, many different kinds of use cases, especially for things like seasonal products or slow-moving products, something like furniture. It makes it very, very difficult to forecast what the inventory needs might be for those kinds of cases. And last but not least, another major drawback to the more traditional methods are the effects that our promotions or sales may have. And I'm going to talk about that on another slide, actually. But in general, all these issues kind of combine to create less accurate forecasting and a much greater risk of mismanaging inventory levels. So with that said, how can ML mitigate or alleviate some of these issues with the more traditional systems? So one thing, and this is again in common with some of the earlier issues that we discussed, we can bring much more data to bear. So things like customer demographics, item promotions, even weather patterns, we can include these things into our data sets that we're going to help use to predict inventory and stock levels. And we can also accommodate highly complex demand patterns and online shopping patterns as well. And as I mentioned, one of the most acute issues with traditional systems are how promotions are forecasted. And essentially with promotions cause supply chain disruptions generally in three ways. And these three ways is right here on the slide. We have cannibalization, the halo effect, and deferred demand. Cannibalization is essentially when one item or product sales decrease as a result of an item of a very similar nature that's going to be promoted. So in other words, I have two types of peanut butter. One is going on sale, one is not. The one that's on sale will probably sell a whole lot more at the expense of my peanut butter that's not on sale. So that's cannibalization. The halo effect is essentially it's when demand increases for items that are related to the items that I'm putting on sale. So for example, if I'm selling a raincoat, I may see an increase in umbrellas or rain boots as a result. And third is the deferred demand scenario. And that's when post our promotion, we're going to see certain kinds of sales decrease on items because our customers already have them. So they were all bought when they were on sale. Traditional rules-based inventory solutions, they have a lot of trouble kind of handling these effects. These kinds of more complex scenarios is exactly where ML solutions shine, and they can really help anticipate these dips or spikes in demand, and they can do it with very little lag time as well, so we can help forecast around these issues and we can forecast more accurately. So an example of this would be Walmart. And Walmart is actually, in so many ways, Walmart's a great example of a lot of what we're talking here today, because Walmart several years ago bought very heavily into the ML solution, into all aspects of their retail strategy. One of the things that they started doing was incorporating weather data into their inventory systems, and they noticed certain increase and decrease in certain kinds of foods. And as Joe mentioned, perishable goods. One of them was under certain specific kinds of weather patterns, they noticed an 18% increase in hamburger sales. And hamburgers is kind of the example we're using here today, but there were a lot of other kinds of food and similar products that they saw these kinds of numbers in. So as a result, they were able to find the patterns in this weather data, correlate that to the kinds of foods that they were selling, and then they were able to use that to predict the supply and demand at the inventory level to stock their stores and online site much, much more efficiently and much, much more accurately, and it saved them quite a bit of money. Now, this, the goal of this webinar is not to dive too deeply into the machine learning algorithms themselves, but some of the more traditional, but we're going to give some examples of some of the more traditional ML algorithms that you see that are leveraged and exploited for inventory optimization. And these four here, going from least to most sophisticated, are linear regression, decision trees, random forests, and ultimately deep learning. And as such, as we briefly discussed with the product recommendation, AWS has a fully managed service called AWS Personalize. AWS also has a fully managed service for more general issues, of which this would be an example of, and that's AWS SageMaker. And so SageMaker, like Personalize, is actually built on top of SageMaker, by the way. But SageMaker is a fully managed service that will help build, train, and deploy your machine learning models. And those algorithms that were in the prior slide, the linear regression, decision trees, deep learning algorithms composed of neural nets, and so forth, SageMaker can accommodate all those types of models based on your need. And it does all the parameter tuning for you, and it will also, most importantly, and this is really important, it continuously monitors your model's effectiveness compared to your actuals over time. And from an operational standpoint, that's very important. So SageMaker is a great way to start plugging in these kinds of approaches into your more traditional inventory optimization control methods.
Buyer segmentation. This is another interesting use case where the traditional means of doing this kind of falls flat. So your traditional means of buyer segmentation, you're going to look at people's age or their gender. You're going to look at their location and try to establish patterns around it, maybe their income level. And what you'll find is when you take your sales data and your customer data and you feed it into an ML engine and say, what are the clusters of users that I have, they tend to cross these lines. They tend to group in unique and interesting ways that you didn't realize. And the commonalities that they have to become part of the cluster are ones that you didn't even think about or realize existed. So why is that important? It's important because when you know what comprises the dissectable or cleanly sliceable group of your users, you can focus on what's effective to market to that user, to build for that user in terms of an experience, what products to stock for that user. And you start to see benefits, revenue and experience, et cetera, across the board from that. So an example that we've seen is when you use an ML-based buyer segmentation system and apply it to discounts and promotions, you can spend less on ads and you can discount less and get a higher conversion rate as a result. So your net effect on margin is significant. Just because if you didn't properly slice that segment before you marketed to it, so you just did it purely on age or gender or location or something like that, there's going to be a percentage of people in that cohort that that message doesn't resonate with. So it really it allows for fine-grained segmentation, not necessarily related to the classic differentiating attributes. The other benefit, obviously, is that it's dynamic. It's not you go in and set your fixed set of segments, and every year you think about it and change it. I mean, you continuously feed the segmentation ML engine, and it will continue to learn. So, Phil, do you want to dive in some on what that looks like practically?
Sure. So, we're just going to add a little bit more detail to some of the things that Joe mentioned. And as he mentioned, traditional segmentation, age, gender, prior product purchases, those are all actual very important aspects of segmenting buyers, but there are some issues. And in many cases, a lot of these categories, they're too broad and they can become quickly outdated. And as almost kind of consistently with some of these other issues that we've discussed in some of the prior areas, they don't take account, again, they don't take account dynamic data. What pages did my customers visit? How long were they on these pages? What links did they click? What kinds of information do we have as part of their profile? A whole lot more than just what was their last purchase, maybe how many purchases they've made and how much they've spent within a certain time frame in the past. So what we want to do is we want to, in order to improve our segmentation efforts, we want to include all this behavioral data. And this is almost a canonical problem in machine learning. And the way we solve this problem is through a class of algorithms that are unsupervised learning algorithms. So generally in machine learning, we have two broad types of algorithms. We have supervised learning algorithms, which are the kinds of things that would be applicable to the problems that we've just discussed: product recommendations, inventory optimizations. And what makes them quote unquote supervised is the fact that we train them with data. We have our data sets, we run them through our models with our training data, and then after that we feed our testing data into it to see how well they've done, and then we tune them and the cycle repeats. Unsupervised learning algorithms don't work that way per se. There is no real training testing step. Essentially, at its bare minimum, we just throw all the data at it and say, do your thing, and then out comes the results. And in this case, the classic unsupervised learning algorithm is based around the concept of clustering. And there's k-means clustering, there's spectral clustering, there's all different ways that we can cluster our data, some more sophisticated than others. But the idea is that we want our machine learning solution to take our data, especially all of our newly acquired behavioral data, and we want it to incorporate that into the clusters of buyers that it's going to create for us and the subgroups that it's going to identify. And the neat thing here is that with a large enough data set, both in terms of volume and width, the amount of data points that we're collecting and the features that we're including in our data sets, it's really interesting the kinds of patterns that these cluster algorithms will find for us. In many ways, they're very counterintuitive. It's very difficult from a manual standpoint to see just what kinds of clusters and information they may take into account for us. However, though, the output is a complete set of segmented buyers that we would have otherwise never had access to as a group. And the outputs for our clustering algorithm can be used. We can feed it we can take a cluster and feed that again into a clustering algorithm, and then we can do things like micro-segmentation and get very, very, very targeted, which could also help with further predictions or forecasts that we'd like to do as well.
Right, so fraud detection, this is usually a constant arms race. You've got scammers out there, or people who want to take advantage of what's supposed to be one-time promotions, or and so on and so on. And they're constantly coming up with new techniques to commit fraud. And the reality is, there becomes a point where you know sometimes it's cheaper to just let a little bit of fraud happen than build a system to fix it. That's never a place you want to be at. So one of the really nice things about using ML for fraud detection is because it's a learning algorithm, essentially the rat race is being raced on your behalf. It continues to learn and continues to detect fraud, and you can just kind of take your hands off the keyboard and let it happen. And that's on top of the fact that it's more effective, and on top of the fact that it does a better job of preventing fraud and preventing it faster. So another great example of, hey, we pick a specific use case and feed it specific data, ML does a great job. Bill?
Thanks, Joe. So to start with, one of the largest Latin America travel companies, Alamundo.com, with introducing ML into their more traditional fraud detection solutions, they were able to reduce fraud and manual reviews by 70%, which is quite a bit. That saves them quite a bit of operational costs over time. So as Joe mentioned, traditional mechanisms, they're typically rule-based. Rule-based systems, they have some drawbacks. And one is, as we tend to include more rules into our systems, we create a much greater opportunity for false positives. So in other words, as the rules get more sophisticated and as we include more rules, we're going to start blocking more genuine transactions than we want. Another drawback is the idea of fixed outcomes. So thresholds for rules they'll change over time, and that can invalidate earlier rules or current rules. And that's going to be very difficult to manage and capture the kinds of transactions that we're looking for. And then last and most importantly is the idea of imbalanced data. Typically with e-com data sets, retail data sets, the overwhelming majority of transactions are not fraudulent. So we have a very, very small percentage of fraudulent data compared to our overall data set. So in order to build an effective fraud detection mechanism, to account for that imbalanced data, we have to kind of include some more sophisticated statistical techniques, and those kinds of things are very difficult to work with a more rules-based system. So by introducing ML into our fraud solutions, we're able to mitigate a lot of those problems that we see with the rules-based system. And the nice thing about this is that the kinds of ML systems that have been in place for this kind of problem have been in place for a very, very long time. This is a classic classification problem similar to spam detection. Is an email spam or is it not spam? So it's similar here. Is a transaction fraudulent or is it not? These kinds of algorithms have been in use for a very long time and they're very mature. They're also much better, again, at handling the idea of this imbalanced data in our data set. Even with a small amount of fraudulent transactions in aggregate, they're able to train themselves to handle that without any additional overhead that might be required with a traditional rules-based system. So, like our product recommendations and our inventory optimizations, a great way to get started to leverage ML solutions in your own retail applications is by taking advantage of available native cloud services. And AWS has one called AWS Fraud Detector. And I'm not going to get into some of the benefits that I've already gotten into because they piggyback off of SageMaker and Personalize in terms of automate the training, the testing, the deployment, and whatnot. The real key differentiator here is that it's been trained on Amazon's own 20-year e-com data set of transactions. And my guess is that in many cases that data set may be larger than most, so it's really going to be tuned well. And in addition to Amazon's own data, of course you can bring your own data into for the training and testing purposes as well. Very easy to integrate. It integrates right into your checkout flows, and it also works with guest checkout scenarios as well. So it's definitely something that you may want to keep in mind when you're going down this route.
All right, so next we're going to talk about some do's and don'ts and basic guidelines to follow when you're starting on ML, and these apply across all of the different use cases that we discussed. So data science and ML is not a silver bullet. This is one that I can't stress enough. You can't just say, let's take any old set of data, let's throw it into a computer, and magically a result will appear. These algorithms work really, really well. They're way more effective than expert systems or people. But you have to use them as they're intended to be used. You have to know what the data looks like that should go into the algorithm and what the expected output is. So don't expect it to be a silver bullet. Know that if your use case aligns, you'll get great results with it. So develop clear questions and goals, and that's just kind of going back to what I was alluding to earlier. If your goals have to be specific enough that the ML algorithm can optimize for them. And you have to have a success metric or a learning metric that actually does improve the results you're looking for. If that's too broad or not done correctly, the algorithm won't learn. The more data, the better. You can't expect a machine learning algorithm to learn on 20 pieces of data. It can need in the hundreds of thousands to millions of data points to be able to learn from to be effective, with the notable exception being if you're using some of the cloud services already have some of their own data points that you can piggyback on, fraud detection being an example of that. So that's kind of a cool head start that you get using some of the cloud services. And sometimes they'll prime the pump for you in terms of having data. And then also be sure to experiment with different ML models. Everybody's situation and data can be slightly different, and there may be models that are more effective for your specific use case and your specific set of data than others.
Okay, so for some don'ts, and our first one would be don't underestimate the time needed for data prep and engineering. Quite a lot goes into this, and ingesting data from various different data sources, cleaning it, prepping it, transforming it, making sure it's accurate, making sure null values are handled correctly, making sure missing data is handled correctly. There's a lot to this, and the bulk of your ML efforts are actually going to be spent on this step here. Building data engineering and ETL pipelines to get your source data into ultimately the machine learning systems it's going to be time consuming, and you don't want to underestimate or short shrift that particular step in the process. Also, don't forget to a little further down the ways, don't forget to monitor the performance of the model's predictions based on your actuals. So now you have your model deployed and you're seeing some benefits and things are working, but that doesn't mean you just stop and you're all set. It's really important to test the forecasting against your actuals over time and see how things are performing, and then possibly go back to that train, test, tune loop if needed. And our final one, and I think this is really important, is if you're first starting out and you don't have a data science department, you don't have a staff of data engineers, you don't have a lot of the quantitative knowledge in-house at this point, don't reinvent the wheel and don't try to build these things yourself. Definitely, where possible, leverage existing managed cloud-native services, and they will bring you a whole lot closer to the finish line. In some cases, 90-95% of the way there. I do implore you to leverage those systems as much as possible. And while you're doing that, you can take your time and build the kind of in-house expertise that you may need to want to go off on more sophisticated paths.
Thank you, Phil and Joe. With that, the presentation portion of our webinar is complete. But before we open up to questions, I'd like to let you know about the JBS Quick Launch Lab. If you're ready to quantify what it'll take to add initiatives like machine learning to your current offerings, but aren't exactly sure where to start, JBS Quick Launch Lab will deliver an approximate timeline, approximate cost, an outline of high-level requirements. We will also recommend an architecture specifically tailored to your business objectives. It's a great way to get started on your new initiatives, and it's completely free. So if you'd like to learn more, please feel free to reach out to us for that. At this time, we'll open it up for questions, and I believe we have a couple in the queue already. If you have questions, please leave them in the chat. We'll answer them in the order they're received. If you don't have any questions at this time, please feel free to drop off or stick around if you'd like to hear what others are asking. Our first question is from Jenny. It says, how long does it take to implement ML before you start to see tangible results?
Okay, it's a good question. And so the reality is it depends on what your goals are, and it depends on your available data. If you have decent available data, and as Joe mentioned, in retail, having sales data and customer data and product data you're probably going to have a pretty decent amount of that data already in your existing system. So that certainly will help speed things along. But if you have fairly modest goals, you want to forecast things for a particular sale, or if you want to incorporate something like fraud detection, for example, where we already have existing managed services, you can get up and running in a few weeks and you can make some real progress.
We've actually done fraud. No, we've done fraud in a day. Fraud is one of those ones where a lot of the vendors come with the pump primed for you on the Amazon side. Obviously, Amazon sees a lot of attempts at fraud, so they have a much larger data set to go with. So something like that, you can go pretty quick.
Now, also, if you want to do more specialized and more sophisticated kinds of ML, where you get more into specialized data collection and much more heavier data engineering with much more sophisticated transformations, and you want higher accuracy thresholds and complex model tuning and so on and so forth, projects like that can take months. So it really depends on what your goals are, but you could get things up and running within weeks to months.
Great. We have another question. What is a model in terms of ML? We heard you reference that a couple times.
Sure.
Is that like a database model?
No, it's not like a database model. The word model in ML parlance, so to speak, it's actually the output of the machine learning algorithm after it's been trained. So it's essentially the data plus the algorithm that's going to do the prediction. And really, at its heart, really what it is it represents what was learned by the algorithm through the training phase with the data that we fed it.
Okay, good. I think we got one more. At one point in the presentation, they're asking that you had mentioned quirks that you need to watch out for in machine learning. So I think what they're asking here is what sort of things are gotchas that you need to be prepared for in the machine learning?
Okay, and that's a great question because there are some definite things to look out for. And in no particular order, some algorithms may work better than others with certain kinds of data. So sometimes the bulk of your data may be text data, other times the bulk of your data may be numerical data, and certain algorithms handle that better. So if you naively just select some algorithm and you're not quite getting the results that you want, it can be based on the kinds of data that you're feeding it, and you may have to experiment until you find one that gives you the results that you want. Another quirk is that certain kinds of algorithms are more prone to what in machine learning we call the over-underfitting situation, and that is where we train models with a data set that's so tied to certain specific things that our model accurately predicts everything on our training data set, but when we go to test it with data that it's never seen before, it falls completely apart. So you want to make sure, and certain algorithms are more prone or less forgiving to that than others. So when you do your test and training, you want to take those kinds of things into account. And the last thing that I'll mention is when you get into more sophisticated approaches, especially things like neural nets and deep learning and reinforcement learning and some of the ensemble learning type algorithms, sometimes it's very difficult to know what's going on under the hood. And with that additional level of sophistication, which also gives better results, you do take a hit in what we refer to as explainability. And it becomes very difficult to explain why my model got the results that it did. It works and it works well, but it may be very difficult to explain just why it's working, as opposed to some of the less sophisticated methods, something like a decision tree, which is essentially just a set of if-else branches, and you can always see, oh, it's making this if here, and it's elsing here. It's very explainable.
Thanks, Phil. I think we got time for one more question. Using the tools from AWS, once a model has been trained, what is provided to the engineer/data scientist to see how the model is built? What are the key or strong features used by the model, and how can you check if there is bias in the model?
So within the console that allows you to build your models, AWS provides a set of tools as part of their AWS console that you can use to garner all those insights in the model. And it's all part, so they offer tools for hyperparameter tuning, the bias variance, and that comes along with the monitoring and the logging and so forth. So you're given a whole suite of graphical tools and dashboards that you can use to monitor how well your model is performing and how they're taking these things into account. And then you can tune or go through the train test cycle. Again, if you're seeing results that you're not pleased with.
Okay. I think that's about all the time we have for today. So I'd like to thank you for attending, and if there's any questions or things you need further explanation on, please feel free to reach out. And I guess at this time we'll end the presentation. Thank you.